Now, suppose we have to prove this. Find the value of f of 2 that makes the function continuous at x equals 2. Now, you notice something a little bit weird here, don't you? What does this factor to? Well, on top we have x plus 9 times x minus 3. And on the bottom, x plus 3 times x minus 3. So the first thing you should probably think of is, wait a second, there's no domain restriction at x equals 2. So why is this function like this? Well, okay, suppose we have some sort of curve or other. This is not what this actually looks like, not even close. But suppose we have some sort of curve. And then you're told, okay, suppose we say that, oh, the domain's different here. And then what do you have to do? You have to fill it in by specifying a value. Well then, that's what we're doing here. So, this is equal to, well, f of 2 is equal to 2 plus 9, 2 plus 3 will fill the domain gap specified. Okay, so this is going to be 2 plus 9 is 11 over 5, which is equal to 2.2. This will make the function continuous at x equals 2 because ensures f of 2 is equal to limit as x approaches 2 of f of x. So that will make it continuous. Alright, now let's graph these functions and describe discontinuities where applicable. So in A we have 9 to the absolute value of x minus 1 over x. And in the second one we get rid of the absolute value. What does the absolute value tell you? Well, it tells you that there's going to be some manner of symmetry involved. Now the top here, this here, 9 to the power of x minus 1 has no symmetry. 9 to the absolute value of x minus 1 though, well, that's an even function. And x, that's an odd function, which means even divided by odd, you're going to end up with an odd function that's symmetrical across 0, 0. Now, honestly, this here should be a blank circle, but, well, there are certain software limitations involved. So, this has a discontinuity, whereas this curve here doesn't. This curve here goes up on toward infinity. It goes toward infinity in the numerator much faster than it does in the denominator. Hence why overall it goes toward infinity as x increases to positive infinity. And here, well, we can see a point of continuity. Is there another word for this? Or another term? Well, yeah. Okay. We can call this removable discontinuity. At x equals 0. And the rest, well, as we can see, it's continuous except at x equals 0. Okay, so what are the other types of discontinuities? There are the obvious big gaps, like this, for example, or fill that in. So, domain gaps. There's infinite discontinuity. So in other words, either we end up diverging, or we can go toward positive infinity or negative infinity. It's discontinuous either way because those are not considered real values. And what else? There's jump, or step, or terminology may vary. Usually jump discontinuity, where you go, oh, curve, 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 sudden jump to another curve, and then you go on. All right. Okay, if f of x is continuous on some closed interval from a to b, and, well, between f of a and f of b there is some value, or between f of a and f of b there is some value c, then there must be some place where, okay, we wrote this as y0, but, well, y equals f of x, we might as well just write it as f of c. It doesn't particularly matter. The point is here that, hey, if you can draw a line from this point, a f of a, to b f of b, without lifting your pencil off the paper, first of all, we know that the x coordinates, or, okay, this axis, the horizontal axis, it's going to end up having a line that covers all the way across. So from A to B. Okay, there's no interruptions on the domain. Fine. What about on the range? Well, okay, we have to get from here to there somehow. So that means every single range value is also covered. Which means that if you have some value between FA and FB, then there is some C value that it corresponds to between A and B. Does this sound okay to everybody? Well, I hope so, because to get from here to there without, say, ever lifting your foot off the ground, well, you're going to end up smudging over every horizontal coordinate on the grid at some point between these two, and every vertical coordinate as well. Of course, I would recommend not doing this with your actual feet and just trying this out if you are inclined to do so on, say, a piece of paper instead, although I hope we don't have to. Example 4. Identify where each of the following graphs is discontinuous, using limits to support your answer. State whether the discontinuity is a jump, infinite, or removable discontinuity. Here, it's obviously discontinuous at x equals -2. At x equals -2. And what type is it? Well, it's a jump discontinuity. Discontinuity. Now, piecewise functions, well, pretty often, feature jump discontinuities. A special type of piecewise function, a step function, where every single line segment is horizontal, so every single segment is a constant, well, that's full of jump discontinuities. So we have, well, here we have infinite discontinuity at x equals 2 and x equals negative 6. Infinite discontinuity at x equals 2 and x equals negative 6. Okay, please remember that even if they both go toward positive infinity or both negative infinity, that's still an infinite discontinuity. Because the domain doesn't cover that point and it goes to infinity one way or another. Now here we have just 1 point taken out of this line. So this is removable. Now if there was a value here specified somewhere, well, this is still going to be removable because, well, that value has been removed to somewhere else as opposed to just removed outright. So that's one way we can think of it. So this is removable discontinuity at x equals negative 2. All right. In summary, the limit of a function at x equals a may exist even if the function is discontinuous at x equals a, such as with a removable discontinuity. On the other hand, a jump discontinuity, the limit doesn't exist at that value. The graph of a discontinuous function cannot be drawn without lifting your pencil. Functions may have 3 different types of discontinuities: jump, infinite, or removable. So just take a line, take out 1 point. Now this 1 point can be put somewhere else, or it can be just not there. So not in the domain. When we directly substitute and get an indeterminate form, we need to determine an equivalent function that represents f of x for all values other than x equals a. For example, the good old difference of squares, except this time we're going to use this instead of -1 and -1. Okay, so this, when we substitute x equals 2, what do we get? We get 0 over 0. Which is indeterminate. Now if we got undefined instead, as in something over 0, well, that tends to asymptote. On the other hand, if we get 0 over something, then all we do is, oh hey, the value is 0. Okay, so the discontinuity can be removed, in quote marks, in this fashion by applying one of the following methods: factoring, rationalizing the numerator or denominator, or expanding and simplifying. It can also be done by certain other methods, such as the one we showed up there, which was basically reasoning on, okay, the ratio between these is approaching 1 as we approach x equals 0. Therefore, as x approaches 0, the limit of the ratio is 1, and that's it. Now, depending on strictness of teacher, perhaps we should have shown that thing earlier from both the positive and negative sides. but we did. Why? Perhaps we should have shown them separately. Why did we actually already show it? We showed, instead of, oh, plus x1 or minus x1, we put delta x. So change in x. Now, please make sure that you know what your teacher likes. Otherwise, well, please state, for say contests, what all your variables are. Otherwise, the guys who mark your stuff, well, they really don't have that much invested in you usually. And, well, I think you get the idea. You need to state what your variables are. Even if you're dealing with people who are trying to fight for your marks, such as, well, at Olympiads, as in like the math Olympiad or the biology Olympiad or the physics or chemistry Olympiads, well, the team leaders, yeah, they do mark your stuff after the official markers do. And then they have to argue to give you extra marks on certain problems. But, well, if you don't explain what your variables are, it's kind of hard for them to keep track of what you're doing sometimes. I say this from experience, trying to mark physics exams. And, well, it's kind of hard to argue. So, please make sure that all your writing is clear. Practice handwriting if you have to. And, of course, you note down what variables you use actually mean. Although I do note that delta x is change in x. Delta symbol, yeah, you don't need to show what that is because, well, the convention is that that's for change. So we'll get to delta very soon. Why? It's because once we actually get into derivatives, the very common dx, or more specifically dy over dx, so change in y over change in x. I wonder what that sounds like. Well, this notation more specifically refers to the derivative. But the derivative is just a function that tells you how another function behaves in terms of its slope. So, this is change in y over an infinitesimally small range over change in x in that same infinitesimal range. So in other words, the slope at any given point or any given x value. This can be written as delta y over delta x. I mean, yeah, it's usually dy over dx, but sometimes you do see this. And there are many other applications of delta for change, such as, oh, hey guys, remember physics class? When we had to calculate speed, we used delta d, so change in distance, over delta t, so change in time. Please note that if you put vectors on these, it becomes velocity and displacement, respectively. Alright, so that's it for now. And next time, we'll get started on derivatives.